Now we'll get to have some fun with this. We created the row average outsider temperature and the average outsider temperature values in structure and we bound them to the same variables in the program that were numeric outputs. Since our program it's already up and running and calculating these values, we can already see the results are quite stunning. Our average temperature hovers around 55, and except for OA temp number 7, that is actually true. And look at how the skewed average outsider temperature would actually be all the way up to 80, which is a very, very radical difference. And in this kind of difference in any averaging, min, max, or any kind of aggregate operation on large sets of data or even small sets of data, this could have significant consequences, these kinds of issues in the way the unit gets controlled. So essentially this is a clear indication, but let's go ahead, it's a clear indication that this is working as we want it. But let's go ahead and trace this out. Okay, we're filling in the OA temps array. We went ahead and did our standard deviation. No need to see this anymore. That's zeroing out the working list, just in case this wasn't the first time we're running the program. So since it was, couldn't tell. Now we're filling in the working list with values from the outsider temperature from the OA temps array, obviously not counting the one that I2 is currently iterating through. So you will notice that the one that doesn't get any values in working list is actually the one that I, in this case, is working with currently. So in this case, we were working on 2. Now we're working on element number 3. So now 3 will be the one that in the working list stays at 0. So N is the one that loops through currently. Now we're doing W, we're cleaning up the working list. And now I is in 4, element number 4 of the OA temps. 4 is the one that gets skipped, as we saw. And so 4 gets a standard deviation and I goes to 5. And now we're cleaning up again. Now we're gonna go ahead and single out 5. 5 won't get a value. Now we calculate that standard deviation, pass it to element number 5 or standard deviations array, and clean up. So we did see a lot of this when we initially did the testing. As you saw, we built this algorithm in parts. We were able to define 3 very specific processes that made up the complete algorithm at the end. This lends itself well to not only actively singling out and dropping the bad values off of the list of values before we perform any aggregate calculations with the list of values, but it also lends itself out well since it maps out exactly which value that is to create another array list of string variables, or actually string constants, with the actual name or description that can be an error message. And since the array list for the string constants would be also 10 elements, and it would map out quite well to all the other arrays we've worked with so far, once we single out the bad one, then we just map it to the same message on the strings array, and now we get ourselves a very granular, very detailed message of which of these elements in the set of data is the bad one. This is quite useful when you with the larger the data set, the more amount elements you have, the more useful this becomes and the more necessary it is. Mind you, you can actually only do this with as little as 3 elements in your list. This would not work with 2 elements in your list, because you need to have a majority vote. That's what the quorum does, is you need to have a majority of the good items versus the minority of bad items in order to identify which ones are good or bad. The basics of the quorum algorithm is the majority of items that are the same are designated as the good values and the values that get replicated and get used, and the minority of very dissimilar values in the data set are the values that get discarded as bad. So if you have the same amount of different values from the other values, you couldn't possibly tell. You don't have a clear majority. So if you had, for example, the possibility of having 2 bad sensors going bad at the same time, and you wanted to discard both of them from the calculation, you would need at least 5 elements in your array list. Otherwise, if you only had 4 and you lose 2, you'd find yourself in the same place where you don't have a clear majority, hence you cannot determine which is the good set of values and which is the bad set of values, and so on. For every a number of values that could possibly go bad at the same time, you have to have enough values on that list to have a clear majority always. So if 3 were to go wrong, you'd have to have 7 in your list, and so on. So at this point, all the standard deviation items have been all the standard deviations have been set. We got a clear very dissimilar value, very different standard deviation from the rest here, quite obvious. And right now we're working through this algorithm, this portion of the algorithm, the last part actually, that is determining if I have more than 2 instances where I'm quite different from my peers in the list. And eventually, when we get to 7, we should put a item in the deviation items array. See how by looking at the placeholder variables, you can tell which loop is executing and which iteration it's going through. You can see that I2 is currently at its 5th iterations, all these loops, obviously, they're just looping through the arrays, so they're only going to have as many iterations as the arrays has elements. So you can see how the for loop running the I2 variable, it's currently at the 6th element. The N2 is currently at its 6th element as well, and W2 is running pretty fast. So once N2 iterates through its 10th element, then I2 is gonna move over to 7, and then at that point we will have a 7th deviation item once we get to N2 and so on. So right now you've seen how C2 has had one, but never too many, never more than one, more than two. See here we have one, very different again, between 6 and N2 and 9, but never two or more than two. More than two would be what actually trigger discarding that sensor value. So now N2 is at 10. So you can see how W2 is the loop executing inside N2, and N2 is actually executing inside I2. So now we're at element number 7. N2 is at 0. So now C2 is already counted at 1. Meaning the 7th element in I2 in the I2 loop is different than the first element in the N2 loop. Now we've counted 2, meaning the 7th element in I2, which is OA temp 7 basically. It's proving to be different than the next outsider temperature sensor value that's being tested in the N2 loop. Now we've got 3. So basically we're that this 7th element of the I2 loop, which is the 7th element of the OA times array, is proving out to be quite different than every other sensor in the OA times array. C2 is at 4 now. See, none of the other elements had exhibited this behavior. And so now we have gone ahead and said, yeah, we've got too many hits on 7, so we're gonna discard 7. So we sent it to the trash list basically, which is this deviation items list. Okay, so we've now reached finally the end of the algorithm portion of the program, and we're now using the results of that algorithm, which is this 7th element of the deviation items array list, which maps out exactly to the 7th element of the OA times array. So if now we had another array of 10 elements with 10 messages or labels for the name, the outdoor temperature sensor by name and location in the building, for example, we could also map that out and use it to output an alarm message or a warning message describing the sensor that went bad, the value that it's reading, the last time it read a good value maybe, or the last time it read a bad value, and where it's located in the building, for example. So and then we calculate our averages, raw and